Hi everyone, myself Dhanalakshmi. Welcome to session 2 of chapter 1 sets of +1 mathematics. In the last session we discussed about the definition of the set, representation of the set in roster and set builder form, and the different types of sets, equal sets. In this session we are going to discuss about equivalent sets, subsets, proper subsets, power set, universal set. Let's see one by one. Equivalent sets. Let's see this equivalent sets through an example. Let A be the set of natural numbers less than 6 and B the set of vowels in English alphabets. Let's write the sets A and B in the roster form. So A will be equal to the set 1, 2, 3, 4, 5 and set B will be equal to the vowels, the set A, E, I, O, U. Now what do we see in this? The number of elements in A is 5 and the number of elements in B is also 5. So we see that n of A is equal to n of B is equal to 5. Hence it is called as equivalent sets. So we can define equivalent sets in this way. Two sets A and B are said to be equivalent if n of A is equal to n of B. We'll do one more example. Let A be the set of days in a week. B be the set of natural numbers such that x squared is less than 50. So let's write in the roster form. So the set A will be equal to the 7 days: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday and Sunday. So 7 days in a week, so n of A is equal to 7. Now the B set, the condition is the square of that natural number should be less than 50. So what are the numbers do we have? 1 square, 2 square, 3 square, 4 square, 5 square, 6 square, 7 square. Square of these numbers are less than 50. Therefore, B is the set 1, 2, 3, 4, 5, 6, 7 whose square is less than 50. So comparing these two sets, what do we see? There are 7 elements in A and 7 elements in B. So what do we conclude? N of A is equal to n of B. Hence we see that A and B are equivalent sets. Next let's move on to the subsets. Let A is equal to 1, 4, 6 and B is equal to the set 1, 2, 3, 4, 5, 6. So what do we see in those sets? 1 is in A, 1 is also in B, 4 is in A, 4 is also in B, 6 belongs to A, 6 also belongs to B, which means every element of set A also belongs to B. Therefore, we see that A is the subset of B and is expressed in this symbol. This symbol is also read as A is a subset of B or A is contained in B. Therefore, we can define the subsets in this way. A set A is said to be a subset of a set B if every element of A is also an element of B. In other words, A is a subset of B if whenever A belongs to capital A, then A belongs to the set B also. This can be expressed symbolically in this way, which can be read as A is the subset of B if A belongs to A implies A belongs to B. So this symbol is called as implies. So A is a subset of B if A belongs to the set A implies A belongs to the set B. If A is not a subset of B, we write in this way. We can also say A is not contained in B. Now let's see to some examples. Example 1. Let A be the set of all divisors of 36 and B be the set of all prime divisors of 36. So, we will write down A and B in the roster form. So, A can be written as, what are the divisors of 36? 1, 2, 3, 4, 6, 9, 12, 18, 36. So, divisors of 36 are represented in the set notation. And in this, what are the prime divisors? 2 is a prime number and 3 is a prime number. Therefore, our set B can be written as set 2, 3. Now, what do we see? The elements in A are not fully in B, but the elements of B are fully present in the set A. So, in this, what can we say that B is the subset of A, as 2 is in B, 2 is in A, 3 is in B, 3 is in A. So, we say that B is the subset of A. Let us go to the next example. Let A be the set of vowels A, E, I, O, U and B be the set A, B, C, D. So, we can see that not all elements in A belongs to B and not all elements in B belongs to A. Therefore, we conclude A is not the subset of B and B is not the subset of A. Next example 3. Let A be the set A, B, C, D. B be the set B, D, A, C. So, compare the two sets. What do we see? A is present in both the sets. B is present in both the sets. C is also present in both the sets and D is also present in both the sets. So, what can we say? A is the subset of B and B is the subset of A. Therefore, we can conclude A is equal to B. So, in other words, we can say the A and B are said to be equal sets because they have the same member or same elements in both the sets. Another example, let A is equal to the set 1, 3, 5 and B be the set of odd natural numbers less than 6. So, we can see that A is set 1, 3, 5, B is the set 1, 3, 5. We can see that the elements of A are in B and all the elements of B are also in A. So, what do we conclude? A is the subset of B and B is the subset of A. Therefore, A is equal to B. Some points to remember. First, we say that empty set is the subset of every set. Because empty set means we don't have any elements in that set. So, we cannot check whether it is present in this set or not. Since we are not sure to prove that the element is not present in the second set, we conclude that empty set is a subset of every set, which is written as phi is a subset of A. Second important point which you have to remember is set 1, 2, 3, 4 is a subset of set 1, 2, 3, 4. In other words, every set A is a subset of itself, which is written as A is a subset of A. So, from the above 2 points, we come to know that every set has 2 subsets. One is null set, another is full set, for sure. Therefore, we can call that phi and A as trivial subsets of A. If a set has only one element, we call it as a singleton set. For example, if you are asked to give an example of the set of even prime numbers, we know that 2 is the only even prime number, which is written as singleton set 2. Next, we will see to the proper subsets. Let us take an example. Let A is equal to set 1, 2, 3. B is equal to set 1, 2, 3, 4. 1 is in A, 1 is also B. 2 belongs to A, 2 belongs to B. 3 belongs to A, 3 belongs to B. But 4 is only in B but not in A. That is, we conclude that A is the subset of B, but A is not equal to B. Like in lower classes, we have studied proper fraction. For example, 3 by 5. That's called as proper fraction because the numerator is less than the denominator. Similarly, here we call this as a proper subset. If A is subset of B or contained in B, but it is not equal to B, then A is called as the proper subset of B and B is called as the superset of A. Let's see to an example. Set 1, 2, 3 is a proper subset of set 1, 2, 3, 4, 5 because all the elements of the first set is present in the second set. Therefore, we can say set 1, 2, 3 is a proper subset of set 1, 2, 3, 4, 5. Next example, set 1, 2 is not a proper subset of set 1, 2. Why do we say that? Because the proper subset should not be equal. If A is a proper subset of B, as per the definition, A should be the subset of B but A should not be equal to B. Here 1, 2 is equal to the set 1, 2. So, we say that the set 1, 2 is not a proper subset of set 1, 2. Now, let us discuss the subsets of the set of real numbers, which you are very familiar with, which you have learnt in lower classes. Let us see one by one. First, we say that the set of natural numbers, which is denoted by capital N and which starts from 1, set 1, 2, 3, 4, etc. is a subset of the real numbers. Next, set of whole numbers, which is denoted by capital W and which starts with the value 0. So, set 0, 1, 2, 3, etc. is another subset of real numbers. Next, set of integers, which is denoted by capital Z, which takes both negative values and positive values. So, we write as -2, -1, 0, 1, 2, etc. It goes on. Next, set of rational numbers. The rational number is nothing but which can be written in the form P by Q, where P and Q are both integers and Q is not equal to 0. That is also a subset of real numbers. Next is the set of irrational numbers denoted by capital T. What do you mean by irrational numbers? It is nothing but set of all x such that x is a real number and x does not belong to the set of rational numbers. Okay. So, all these are subsets of real numbers and we should also note that N is the proper subset of W, is a proper subset of Z, which is a proper subset of Q and it is a proper set of the real numbers R. You can also see the elements of T belongs to R. So, I can say T is a subset of R. Also, we can see that Q is not the subset of T. Similarly, a natural number is also not the subset of the irrational numbers. These are the few examples connected with the subsets. Problem 1. If A is equal to empty set, write all the subsets of A. If A is equal to empty set, naturally we know that every set has got two subsets. One is null set, another is full set. So, here A is just the empty set. So, the subsets will be only the null set. So, answer is 5. Therefore, number of subsets is equal to 1. Problem 2. Let A be the set 1. Write down its subsets. Again, as per the theory, empty set is one subset and the full set, the given set is one subset. So, there are two subsets, they are phi and singleton 1. Therefore, number of subsets is equal to 2. So, when A has got one element, number of subsets will be equal to 2. Now, let us go to the next example where A is set 1, 2. Write all the subsets of A. So, you know that empty set is a subset of every set. Then we take one element at a time, then we take the full set. So, let us see. Therefore, the answer will be empty set, singleton set 1, singleton set 2, we are taking one at a time, then together the full set, set 1, 2. So, how many are they? When A has got 2 elements, the number of subsets is equal to 4, which is nothing but 2 square. Let us go to the next problem. If A is equal to set 1, 2, 3, write all the subsets of A. So, we always begin with the empty set, then set containing one element, then set containing 2 elements, then the full set. So, we will do one by one. So, 5, set 1, set 2, set 3. So, we have taken one at a time. Now, we will take 2, 2 together, set 1, 2, set 1, 3, set 2, 3. Now, finally, the full set, set 1, 2, 3. So, how many are there? 8, which means if A has got 3 elements, the number of subsets is equal to 8, which we can write it as 2 cube. So, in general, we can say that if A has got m elements, then the number of subsets is equal to 2 raised to m. If A has got m elements, then the number of subsets of a set A is equal to 2 raised to m. Okay. Next, we will move on to the power set. So, in the last 4 problems, we discussed about the subsets of a set. If all these subsets are enclosed within braces, we call that as a power set. Therefore, power set can be defined as the collection or the set of all subsets of a set A, and it is denoted by capital P of A. Once again, I will say it. The power set is defined as the collection or set of all the subsets of A, which is denoted by capital P of A. So, we will take the example. If the set A is equal to 1, 2, write the power set of A. So, the power set is nothing but the subsets which is enclosed within the braces. So, it is set of all subsets. Let us open the set notation. So, for 1, 2 we know that empty set, set containing one element, then full set. So, we get 5, set 1, set 2, set 1, 2. So, how many elements are there in the power set? We have got 4 elements, which is nothing but 2 square. Let us go to the next example. Set A is equal to 1, 2, 3. Write the power set of A. Again, the power set is nothing but the set of all subsets. Just now we did that problem. We have to just put within the set notation. So, first we will take empty set 5, then one at a time, then 2 elements together, finally the full set. So, we will write one by one. So, P of A is equal to, open the set notation. Now, write down the subsets 5, set 1, set 2, set 3, set 1, 2, set 1, 3, set 2, 3. Now, finally coming to the full set, set 1, 2, 3. So, how many are there? So, the number of elements in the power set is equal to 8, which we can say it as 2 cube. Let us move on to the next problem. If A is equal to set 1, 2, 3, 4, what are the power sets of A? How many elements will be there in the power set of A? So, let us see. P of A is equal to, first open the set notation, first empty set 5, then one at a time, set 1, set 2, set 3, set 4, over. Now, we are going to combine two elements, set 1, 2, set 1, 3, set 1, 4. So go in the systematic order, complete all possibilities with the elements starting with 1. Now come to 2, 2, 3, set 2, 4. So with 2 also it is over. Next set 3, 4. So 2 sets are over. Now we'll take 3 elements at a time. Starting with 1, what are the possibilities? Set 1, 2, 3, set 1, 2, 4, set 1, 3, 4. So with 1 you get 3 possibilities, set 2, 3, 4. Finally, the full set 1, 2, 3, 4. So how many elements are in power set A? It is nothing but 16, which we can write it as 2 raised to 4. So we can summarize this result as in this tabular column. If A is a set 1, number of elements in A is 1, and just now we did all the problems. So number of subsets is equal to 2. Number of elements in power set is also 2. So we can write it as 2 raised to 1. If A is the set 1, 2, number of elements in the set is 2. Therefore, number of subsets will be 4. And number of elements in P of A is also 4, which we did now, which we can write it as 2 squared. If A is equal to 1, 2, 3, the number of elements in A, otherwise I can say cardinality of A, that is another word, is 3. Number of subsets in A is 8, which we got it now. Number of elements in P of A is nothing but the subsets enclosed within the braces. So it will give the same number 8, which we can write as 2 cube. And the last example which we did was set 1, 2, 3, 4. So number of elements in A is 4. Number of subsets 16. Number of elements in power set is also 16, which we can write it as 2 raised to 4. Therefore, from this box we get some formulas which are very important. We'll see one by one. Therefore, if A is a set with number of elements as m, say n of A is equal to m, then first one, number of subsets of A. From the previous table we know that it is 2 raised to m. Number of elements in power set is also 2 raised to m because they are equal except for the braces. Therefore, what do we see? Number of subsets of a set A is same as number of elements in the power set of A, that is also equal to 2 raised to m. Number of proper subsets of A is nothing but 2 raised to m minus 1, because by proper set we mean that A is the subset of B, but A should not be equal to B. So we will not have the full set. So the formula is 2 raised to m minus 1. Based on this, we'll do few problems now. The first problem, if A has 10 elements, which means m is taken as 10, n of A is 10, then find the number of, first question, subsets of A. So just now we noted some important points. The formula to find the number of subsets of A of having m elements is 2 raised to m. So here m is 10, therefore number of subsets of A is 2 raised to 10, which is 1024. Second question, number of elements in the power set of A. That formula is also 2 raised to m, that is 2 raised to n, 1024. The third question, subsets having exactly one element. So we have got total 10 elements. So if you're going to have one element combination, how many you will have? Set 1, set 2, set 3, set 4, set 5, set 6, set 7, set 8, set 9, set 10. So you will have the answer to be 10. So number of subsets having only one element is 10. Next question. Number of subsets having exactly 2 elements. So A has got 10 elements. So how many 2 elements combination will be there, like 1 2, 1 3, 1 4, 1 5, 2 3, 2 4, 2 5, 5 6, 5 7. So we cannot sit and write all the combination of 2 elements. So for that, out of 10 elements, 2 element subset can be written as 10 into 9 by 2 into 1, which is 45. This will be discussing in detail in chapter 7 called as permutation and combination. There is a direct formula to evaluate this. Similarly, if you want to find the subset having 3 elements, this can be written as 10 into 9 into 8 because we need 3 elements by 3 into 2 into 1, etc. Next, the proper subsets of A. If A has got 10 elements, how many proper subsets of A? Find the number of proper sets. So what is the formula? It is 2 raised to m minus 1. So m is 10, which is 2 raised to 10 minus 1. So what do we get the answer? 1023. Let's go to the next problem. Write all the subsets of the set A, set B. It is not just set A, B, it is set A, set B. So whenever you are asked to write the subsets, we start with the empty subset. So we will write them. So 5, then take one at a time. So set A. When we say set B, just because the set notation is A, it does not mean that just writing set B alone is enough. No. There it is an element. So when we write, it should be written as set B. Because set B is an element here. When we write the subset, we should put another set notation on the full set A, B. Next problem. The proper set has 127 elements. Then find the cardinality of A. So what do you mean by the cardinality of A? The number of elements in A. So let n of A is equal to m. The formula to find the proper subset is 2 raised to m minus 1. Here it is given the number of proper subsets is 127. So what is given to you? 2 raised to m minus 1 is 27 is given to you. And you are asked to find what is m. How many elements are there in that set? In other words, cardinality of A. So let's simplify. 2 raised to m minus 1 is 127, which implies 2 raised to m is 128. That implies 2 raised to m. Since the base is 2 here, the 128 should be written in the powers of 2, which is 2 raised to 7. Therefore, equating the powers, we get m is equal to 7. Therefore, the cardinality of A is 7, which means A has got 7 elements. Next problem. Let A is equal to set 1, 2, set 3, 4, 5. Which of the following statements are incorrect and why? Set 3, 4 is a subset of A. Is it true or false? When we see the set 3, 4 is an element in A. So we can only say set 3, 4 belongs to A. We should not say it is a subset of A. Therefore, it is false. Next question. Set 3, 4 is a subset of A. Of course, set 3, 4 belongs to A. So when you put another set notation, it is a subset of A. It is true. Set 1 to 5 belongs to A. You know that set 1 to 5 is a subset of A. There is no 1 to 5 set coming together. So we can say that set 1 to 5 belonging to A is false, and set 1 to 5 is a subset of A is true. That is true. Next, set 1 to 3 is a subset of A. Is it true or false? 1 is there in set A, 2 element is also there, but there is no separate 3 there. Set 3, 4 is there, but separate 3 is not there. So the set 1, 2, 3 is not a subset of A. So the given statement is false. Next, 5 belongs to A. We know that 5 is an empty set. An empty set is the subset of all the sets. So this statement is wrong since 5 is a subset of A. Next, we'll go to the universal set. Let's consider an example. Let A is equal to set AB, B is equal to set CD, C is equal to set EF, and U is equal to set A, B, C, D, E, F, G, H. Actually, what do we see here? A is a subset of U because AB belongs to U. B is also subset of U. C is also subset of U. So, what do we call U as? U is the superset of all the sets given here because U contains A, set B, set C. Therefore, U is the superset of all the sets. Hence, we can define the universal set as the superset of all the sets under consideration, which is denoted by capital U. We will see to an example. When we talk about the set of natural numbers, whole numbers, integers, rationals and irrationals, all these are contained in the set of real numbers. Therefore, we know that set of real numbers is the universal set. So, in this class, we discussed about the equivalent sets, the subset, proper subsets, power set and universal set. With this, we come to the end of this session. Thank you.